Hey everyone, and welcome back. We're diving into the world of thermal energy storage today.
Ooh, that's a hot topic.
It is. Specifically, how these things called fins can make it way more efficient.
Yeah, they're pretty cool.
You've probably all heard of solar power and electric cars.
Of course.
Well, the research we're looking at today could be a game changer for those technologies and a lot more. I'm going to break down a pretty dense academic article.
Sounds fun.
Don't worry, though. We'll make sure you don't get lost in the weeds and you come away with all the important aha moments.
That's our goal.
So what makes this deep dive so interesting?
Well, we're really talking about a simple technology that could have a big impact on how we all live and use energy.
In a more sustainable way.
Exactly.
Okay, so before we get to the fins, let's talk about the core of these systems.
Okay.
Phase change materials.
They're PCMs.
PCMs.
They're like thermal sponges, PCMs are.
Ooh, I like that.
Yeah.
Yeah.
They absorb a ton of heat when they melt from solid to liquid and then release all that heat when they solidify again.
So like ice melting and then that water freezing back into ice.
Exactly. It's that transition between phases where they really shine.
So instead of the temperature changing, the material itself changes.
Yeah.
That's wild.
It is, and different PCMs melt and solidify at different temperatures.
Oh, that makes sense.
Like good old-fashioned water is a PCM.
Oh, right.
It melts at 0 degrees C.
Which is great for some things, but not for others.
Exactly. Paraffin wax is another common one.
Okay.
That melts around 40, 50 degrees C.
I've heard of that one.
Yeah, which is why it's used a lot in things like thermal regulators for electronics.
So choosing the right PCM depends on what temperature you need to work with.
Yeah.
Like picking the right tool for the job.
Precisely. And the research we're looking at covers a whole bunch of different PCMs.
Really?
Oh, yeah. They even looked at some high-temperature options like potassium nitrate.
Wow.
Which melts at over 300 degrees C.
Now, that's hot.
Yeah.
But you mentioned there's a catch.
There is.
What's the downside of using PCMs?
Well, the catch is that a lot of PCMs are good at storing heat,
Okay.
but they're not so good at transferring it quickly.
So like a thermal battery with a slow charging port.
That's a great way to put it.
That's a problem.
Yeah, and that's where fins come in.
Fins to the rescue.
Exactly. They're like adding a bunch of wider pipes to that bathtub analogy, allowing it to drain or fill way faster.
So how do they actually speed things up?
Fins are basically just extended surfaces that increase the contact area between the PCM and its surroundings.
Okay, so like a radiator with all those metal fins sticking out?
Yeah, exact.
Providing more surface area for the heat to transfer?
Yeah, like thermal superhighways.
I love that. So the research looked at what kind of materials for fins?
They looked at a bunch, but aluminum is the most common.
Because it's cheap.
Well, it is affordable, yeah. But it's also a great heat conductor.
That makes sense.
Yeah.
But I'm guessing it's not as simple as just slapping on any old fin.
Right. You're right. It's
Yeah.
not just about slapping on some metal.
Spill the tea. What kind of fin features did the researchers look at?
One of the key factors is the number of fins, or the fin pitch.
Fin pitch, okay.
Yeah. It's kind of like if you have one candle, it'll take a while to heat a room, right?
Right.
But you add more candles.
More heat faster.
Exactly. More fins generally mean faster melting and solidifying times for the PCM.
Up to a point, I'm guessing.
Exactly.
Too much of a good thing can be bad.
Too many fins can crowd the space and actually block that natural flow of heat.
So it's all about balance.
Yeah.
What other fin features make a difference?
Fin length is another big one.
Okay.
Longer fins generally transfer heat better.
Makes sense.
But if they're too long, they take up too much space and can reduce the amount of PCM you can actually fit into the system.
Right, so it's a trade-off. You need enough fin length for good heat transfer, but not so much that we lose out on PCM storage.
Exactly.
What about fin thickness?
Thickness actually has less of an impact than the number and length of the fins. It's like a single-lane highway can handle a decent amount of traffic, right?
Okay, yeah.
But if you want to really move things along, you need to add more lanes, not just make each lane wider.
So thinner fins are better.
Yeah, they're usually preferred because they use less material and they're lighter.
Which is especially important for things like phones and electric vehicles.
Exactly.
Did they look at the orientation of the fins? Like vertical versus horizontal?
They did. And vertical fins can actually take advantage of something called natural convection.
Okay.
It's like a hot air balloon.
Oh, yeah.
The hot air naturally rises and creates that upward movement.
So vertical fins work with these natural currents.
To improve that heat transfer?
So it's not just sticking fins on randomly. We're being strategic about it.
Absolutely.
For maximum effectiveness.
Yes.
It's like a delicate balancing act.
It really is.
So is there anything beyond these simple straight fins?
There is. There's a whole world beyond those basic fins you might picture.
Ooh, I love this. Give me the cool details.
Well, there are things like annular fins.
Annular fins.
Yeah. They're ring-shaped and commonly seen in heat exchangers.
Okay.
Or longitudinal fins.
Longitudinal.
Yeah, they run along a surface to maximize contact.
Cool.
They even looked at pin fins.
Pin fins.
Yeah, they're small cylindrical ones that stick out because
Okay.
they create a more turbulent flow, which can be really good at speeding up that heat transfer.
Pin fins. So we're adding a little personality to these thermal systems.
A little bit of prickly personality?
But it sounds like there's a method to the madness.
Absolutely. And it gets even crazier. Some researchers are getting even more creative with the shapes.
Are they?
Oh, yeah. We're talking T-shaped, Y-shaped, cross-shaped, even snowflake-shaped fins.
Wow, snowflake-shaped.
It's all about optimizing those heat highways and figuring out the best way to direct that heat flow.
So it's way more complex than I imagined.
It really is.
I'm already picturing a thermal fashion show with fins strutting their stuff down the runway.
That's a great image.
But seriously, this is fascinating stuff. We've only just scratched the surface of fin design here.
We have.
Before we dive deeper into all those intricate details,
Okay.
let's take a break. When we come back, we'll explore how all of this fantastic design actually translates into real-world applications.
Sounds good.
Stay tuned.
Welcome back. I'm still thinking about all those crazy fin shapes we talked about.
Yeah, there are some wild ones out there.
It's amazing how something so simple can have so many variations.
It really shows how creative the researchers are in this field, always pushing the limits to get the best performance.
So before we go too far down that rabbit hole,
Okay.
I'm curious about how this tech could actually be used.
In the real world.
Yeah. What are we talking about here?
Well, one big area is making our homes more energy efficient.
Ooh, that's a big one these days.
It is. And more comfortable, too.
Okay, how?
So imagine a heating and cooling system
Okay.
that uses PCMs to store thermal energy.
Like a thermal battery for your house.
Yeah. During the day, it could soak up that extra heat from the sun.
Like a sponge.
Yeah. And then at night, release that heat to keep your house warm. So no more running the furnace all the time.
Exactly. You could rely on that stored energy to keep things comfy.
Would you need a huge unit, though?
That's a good question. PCMs can actually store a lot of energy in a small space.
Oh, that's good.
So the unit might not be as big as you think. Plus, researchers are working on putting PCMs right into building materials.
Really?
Yeah, like wall panels and ceiling tiles.
So your walls and ceilings could help regulate temperature.
That's the idea.
That's so cool.
And because PCMs release heat at a constant temperature, you wouldn't get those annoying temperature swings you get with a normal thermostat.
No more blasts in the AC just to cool down one room.
Exactly.
That's a win-win. What other applications are there?
Keeping electronics cool is another big one.
Especially as they get more powerful.
Exactly. PCMs with those embedded fins could be huge for preventing overheating.
So no more burning your legs on a laptop
Hopefully not.
or worrying about your phone dying in the heat.
It could even help keep those giant data centers cool.
Oh, wow. Those things generate a ton of heat.
They do. Researchers are looking at a few different ways to use PCMs there.
Okay, like what?
One is using them passively to just absorb the heat.
Like a heat sink.
Exactly. Another is using them as a buffer to kind of smooth out the temperature changes.
So the cooling system wouldn't have to work as hard.
Exactly.
Makes sense with how much we rely on data centers these days.
It does. And this technology could even be used in industrial processes.
Oh, really? Like how?
For waste heat recovery.
Okay.
Imagine a factory that generates a lot of heat as a byproduct.
Lots of industries do that.
Right. Instead of just letting that heat escape,
Yeah.
we could capture it with PCMs.
To reuse it.
Yeah. To heat water or generate electricity or even power other processes in the factory.
So instead of wasting it, we turn it into a resource.
Exactly. Closing the loop.
I like it. So we've talked about all this amazing potential.
Yeah.
But what about the cost? Is this stuff actually affordable?
That's a really important question. And the good news is that the cost of PCMs has been going down.
Oh, that's great.
And as research continues and production scales up, it'll keep getting cheaper.
So like any new technology, it starts out expensive, but as it becomes more common, the price comes down.
Right.
That's good to hear. But are there any other challenges?
Well, one is finding the right PCM for each application.
Okay.
Some of the earlier PCMs weren't so great.
Like what do you mean?
Well, some were toxic or flammable.
Oh, yikes. Not ideal.
Not at all. So researchers are working hard to find safer, non-toxic PCMs.
Ones that won't cause more problems than they solve.
Exactly. They're also looking for materials that are abundant and easy to get.
to avoid supply chain issues.
Right.
A lot to balance performance cost and environmental impact.
It is. And even once you have the right PCM,
Yeah.
there's the challenge of actually integrating it into existing infrastructure.
Oh, right. Making it all work together.
Whether it's a building or a gadget or a factory, it takes some clever engineering.
So it's not just about the tech itself, it's about how we use it.
Exactly.
Wow, this has been an amazing deep dive. We've gone from thermal sponges and fin fashion shows to a vision of a future where waste heat is a valuable resource.
It's exciting stuff.
It is. So what else can you tell me about this tech? What's next?
Well, one of the most exciting areas is bio-inspired design.
Bio-inspired design. Okay, I'm intrigued. What do we mean by that?
Well, what if we could design fins that mimic nature?
Like how?
Think about the veins in a leaf or the patterns on a coral reef.
Wow, nature's pretty amazing.
It is. Those intricate structures,
Yep.
they're incredibly efficient at transferring heat.
That's taking fin design to a whole new level. But wouldn't those shapes be hard to make?
That's where 3D printing comes in.
Ah, of course.
We can create really complex shapes now that we couldn't before.
So we could 3D print fins with all kinds of crazy designs.
Exactly. Microchannels, porous structures, you name it.
So we're not just copying nature, we're learning from it.
Yeah. We're taking those principles and applying them to our designs.
Okay, my mind is officially blown. We've gone from fish fins to snowflake fins to bio-inspired fins. What kind of impact could these new designs have?
They could lead to some really big breakthroughs.
Like what?
Smaller, more powerful batteries for electric vehicles.
Oh, that would be huge.
Imagine a battery that charges in minutes.
That would be a game changer.
Or what about heating and cooling systems that use almost no energy?
That would save so much money and help the environment.
Exactly.
It's amazing to think that something as simple as a fin could be so important.
It really is. It's all about innovation.
So we've covered a lot of ground in this deep dive.
We have.
From the basics of PCMs to some pretty mind-blowing ideas about the future.
It's been a fun journey.
It has. Is there anything else you want to highlight?
I think it's important to remember that this technology isn't just about efficiency.
Okay.
It's about building a more sustainable world.
A world where everyone has access to clean energy.
Exactly. It's about creating a more equitable future for everyone.
Well said. All right, listeners, we've reached the end of our deep dive into thermal energy storage.
I hope you enjoyed it.
We've gone from a dense academic paper to a really interesting conversation about the future of energy and sustainability.
And equity.
It's incredible to think that something as small as a fin could have such a big impact.
It just goes to show that innovation can come from anywhere.
Absolutely. So keep those minds buzzing, and we'll catch you on our next deep dive.